Alright, let's jump right into 12.2. 12.2 talks about arithmetic sequences. Let's begin with a warm-up. Let's find the formula that defines the sequence 1, 4, 7, 10. Go ahead and pause the video, give it a try if you'd like. Alright, so you may have noticed that the first term in this sequence, A1, is 1. A2, the second term in the sequence, is 4. A3 is 7. A4 is 10, and so on. This continues on and on. Do you recognize a pattern between each consecutive term in the sequence? You may have noticed that between terms 1 and 2, we add 3. Between terms 2 and 3, we also add 3. And likewise from terms 3 and 4. This pattern continues throughout the sequence. In particular, this sequence from each term increases by 3 every time. If we were to look at this as a linear function, right, we might say that the slope of this function is 3. And we might say that we've got a point. So the first term in the sequence is at 1. So we might say that we've got the point 1, 1. That first term is 1. We might also say we've got the point 2, 4, 3, 7, 4, 10. For simplicity's sake, we'll use the point 1, 1. We can plug this into point slope. So we have y minus 1 equals 3 times x minus 1. And we simplify, we get y equals 3x minus 2. So if we were to graph this line, any points on this line with natural number x would be terms in this sequence. So if we were to write this as a sequence, we could say that we have an is equal to 3n minus 2. How can we write this as a recursively defined sequence? So as a recursively defined sequence, we would say that our initial point, our initial term, is 1. Furthermore, we have an is that previous term plus 3. We can say an minus 1 is equal to 3 times n minus 1. And to get an by itself, we have an equals 3 times n minus 1 plus 1. Looking at this, what do we notice is the 3, right? We're adding 3 every time. This is the common difference between each term. We call that, we denote that as d. This is the common difference. Where does this 1 come from? Well, this 1 is our initial term. So this is, we call that a, that is our first term. And that's what defines an arithmetic sequence. An arithmetic sequence is a sequence that with each consecutive term, we've got an additive rate of change. We can think of these as increasing linearly. So let's give a formal definition to an arithmetic sequence. An arithmetic sequence is a sequence in the form a, that's the first term. The second term is a plus d. The third term is a plus 2d, a plus 3d, and so on. If you notice in our first example, our first term was 1, and then each term we added 3. So we add 3 once, we get 4, add 3 twice, we get 7, add 3 times, we have 10, and so on. So again, where a is the first term, and d is the common difference. Of the sequence. So I like to think of these similar to linear functions, right? They've got an additive rate of change. The nth term of an arithmetic sequence, so the nth term is given by... So before we write it out, let's see if we can recognize a pattern. Our first term is a, our next term is a plus 1d, our third term is a plus 2d, our fourth term is a plus 3d. What do we notice is happening every time? Well, for any given n, we're going to have a plus some number of d. The first term has 0, the second term has 1, third term has 2, fourth term has 3, so it's always 1 less than the number of terms. So n minus 1 times d. D is called the common difference because any two consecutive terms of an arithmetic sequence differ by d. Alright, let's try a few examples. Example 1, find the first 5 terms and then the nth term of the arithmetic sequence where a equals 2 and d equals 3. So if we were to write out the terms, the first term is a, 2. The next term is a plus d, so 2 plus 3. The next term is a plus 2d. And the next term is a plus 3d, and so on. Right, we can already find the first 5 terms here. We have 2, 5, 8, 11, and 14. We can also use our formula to find each of these terms. Let's find the nth term. An is our a, which is 2, plus n minus 1 times d, which is 3. So we can move that 3 out in front and say 2 plus 3 times the quantity n minus 1. You can put it on the other side. Either way is fine. It's generally understood that this is the product of 3 and the quantity n minus 1. So the nth term and the first 5 terms. Okay. I've given example 2. I'm saying that it's an arithmetic sequence, and I've given you the first 2 terms. I want you to find the first 6 terms and then the 300th term. So we begin with our first term, a, which is 13. And then to find our common difference, we take the difference of any 2 given consecutive terms. So here we have 7 and 13. We're going to take the difference. 7 minus 13 gives us negative 6. I want to find the first 6 terms, so we have 13. The next term is 7. We were given that. The next one is 6 less than that, so 1. And then 6 less. Negative 5, negative 11, and negative 17. These are the first 6 terms. To find the 300th term, we're finding a 300, which is a plus n minus 1, so 300 minus 1, times d, which is negative 6. When we evaluate, we get negative 1,781. Let's try example 3. I've given you an arithmetic sequence whose 11th term is 52, the 19th term is 92, and I want the 1,000th term. So again, I'm just going to write the general form for an arithmetic sequence. We have an equals a plus n minus 1 times d. We know that the 11th term, so a11, is 52. We don't know what a and d are yet, but we know that we're at the 11th term. So plugging that in, we have a plus 11 minus 1 times d, and we know that that's equal to 52. We also know that the 19th term, a19, is, in general, a plus n minus 1, well, we have 19 minus 1 times d, which we don't know. That's equal to 92. Simplifying these 2 equations, we have a plus 10d equals 52, and we have a plus 18d equals 92. So here we have 2 equations with 2 variables. We've got a system of linear equations. So we can find the values for a and d. When we solve this system, we get a equals 2 and d equals 5. You can try that on your own and just verify that those are the correct solutions. So when we plug it in, we want to find the 1,000th term. In general, we have an equals a, which is 2, plus n minus 1 times d, which is 5. We want the 1,000th term, so we're finding a 1,000. We have 2 plus 1,000 minus 1 times 5. 1,000 minus 1 is 999 times 5 plus 2 is 4,997. Okay. Example 4, let's find the sum of the first 8 terms of the sequence. We have 1, 4, 7, 10, 13. This continues from our warm-up. So if I were to write out the first 8 terms, we have 1, 4, 7, 10, 13. What's happening each time? We're adding 3 every time. So from 13, we get 16, 19, 22, and that's the first 8 terms. If we were to add these up, so we take the sum of all of these terms, we get a total sum of 92. Suppose I ask you to find the sum of the first 80 terms. This would be quite tedious to do by hand. So let's discover a way that we can use arithmetic sequences to find the sum of the first n terms. This brings us to partial sums of arithmetic sequences. So it follows pretty similarly to our understanding of partial sums right now. Let's define what a partial sum for an arithmetic sequence is. For the arithmetic sequence, and we'll say an equals a plus n minus 1 times d. That's our definition for an arithmetic sequence. The nth partial sum is given by Sn, it's capital S, equals a plus, so this is the first term, plus the second term, so a plus d, plus the third term, which is a plus 2d, plus the fourth, fifth, sixth, and so on, all the way up to the nth term, which we know is this here. So plus a plus n minus 1 times d. So this is the nth partial sum. This is given by, we have 2 different ways to represent this sum. The first, I have Sn is equal to n over 2 times 2a plus n minus 1 times d. We can also, if we have an, we can also use this formula. We have Sn equals n times a plus an over 2. So of course each of these formulas have their advantages. If you have a and d and n, you can just plug it right in here and find the partial sum for the nth partial sum. If you have n, a, and an, then you can just plug it right into here. So depending on what you have, you can use either one of these formulas. So let's practice finding some partial sums of arithmetic sequences. Example 5. Find the sum of the first 40 terms of the arithmetic sequence. We have 3, 7, 11, 15. So writing this out, our first term is 3. And our common difference, what happens between each term? We're adding 4. So our common difference is 4. Let's try this using the first formula. So Sn is equal to, we want the first 40 terms, so n is 40. So we want the 40 terms, sum of first 40 terms. So this would be S40 is 40 over 2 times 2 times a, which is 3, plus n minus 1, 40 minus 1, times d, which is 4. We have 40 over 2 is 20, times 2 times 3 is 6, plus 40 minus 1 is 39, times 4 is 156. And we evaluate this, we have 3,240. Go ahead and give it a try using formula number 2. Alright, go ahead and check your work. If you used formula number 2, first you need to find an, the arithmetic sequence for the nth term, and then we plug it into our formula number 2, so we have n times a plus an all over 2. We evaluate, we find that we get the same thing. Okay. Let's try example 6. Find the sum of the first 50 odd natural numbers. So writing out just a list, we've got 1, 3, 5, 7, 9, 11, 13, and so on. And the first 50 would be all the way up to 99. If you weren't sure how to get that, you can always find, well, what is the 50th term of the natural odds? So we have our initial term is 1 plus n, which is 50 minus 1. And then what's our common difference? We're going up 2 every time. When we evaluate this, we get 1 plus 98, which is 99. So that's another way that we could find the 50th odd natural number. Let's find the nth partial sum using formula 2. So using formula 2, we have our initial term is 1. Our common difference is 2. So we have Sn equals, we have 50, so sorry, this is S50, times A, which is 1, plus An, which is 1, plus n minus 1, so 50 minus 1 times 2, all over 2. We get 50 times, this would be 100 over 2. So then we have 50 times 50, which gives us 2,500. Alright, let's try a few more examples. Example 7, we have an amphitheater has 50 rows of seats with 30 seats in the first row, 32 seats in the second row, 34 seats in the third row, and so on. Find the total number of seats in the amphitheater. So the initial term, the first term, A, is however many seats in the first row. We have 30. The common difference, how does the number of seats change per row? We add 2. So our common difference is 2. And I want to know what's the total number of seats, or how many seats in 50 rows. So the number of seats is 50 rows. And we want to know the sum of all of the rows. So we'll plug it into our first formula. Sn equals n over 2 times A, which is 30, plus n minus 1, 50 minus 1, times D, 2. So we get 50 over 2 is 25, times 2 times 30 is 60, plus 50 minus 1 is 49, times 2 is 98. Evaluate this, and we get 3,950 seats. Okay. Here I've given you an arithmetic sequence, 5, 7, 9, and I want to know how many terms do you have to add up in this sequence in order to get a partial sum of 572. So we're kind of working backwards here. I've got your initial term, your first term is 5. Your common difference, each time it goes up by 2. And I want to know n. So I'm giving you the partial sum. So it all adds up to 572, and then we plug it back into the formula. So we have n over 2, we're solving for n, times 2 times A, plus n minus 1 times D. Okay, simplifying this, we have 572 is equal to n over 2 times, this would be 10 plus 2n minus 2. Okay, distributing, well, let's do 572 equals, this would be 5n, this would be plus n squared, this would be minus n. So then we have n squared plus 4n, and we'll move that 572 to the other side. Factoring this, we have n times n minus 22 times n plus 26. That's equal to 0. Using the zero product property, we have n equals 22 and n equals negative 26. Now, which solution do we choose? Well, since n is the number of terms in the sequence, we can't use the negative 26, right? The number of terms has to be positive, so we eliminate this answer. Let's go ahead and write that out. So since n is the number of terms in the sequence, n cannot equal negative 26. So then n equals 22. We have to add up the first 22 terms in order to get 572. This is 12.2 arithmetic sequences.